Yeah. So, good afternoon, all of you. I am Simran, a PMRF teaching assistant of the course Introductory Organic Chemistry Second, which is running on the platform of NPTEL. And the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISA Pune. So, here I am taking the sessions on every Sunday at 3 to 4. So, I have prepared some slides for the NMR spectroscopy. So, in this week, we are discussing the problems related to the NMR. So, coming to the problem one, which is the amount of energy available in radio frequency radiation is sufficient for which of the following? So, the options are excite an atom, vibrate a molecule, or affect the nuclear spin of the atom. So before answering this, we first have to know that what is the radio frequency radiation and what is the amount of energy which is related to these kind of radiations. So we need to see the electromagnetic spectrum which is there. So here, from here, we can see that the radio frequency waves are the higher frequency, higher wavelength and low frequency radiations. So as we are going from radio frequency range to gamma rays, the wavelength is decreasing. But when we are going from radio waves to gamma rays, then the frequency of the rays are decreasing dramatically. So now we get the idea that these are the higher in wavelength and lower frequency radiations. So now we have to relate these information to collect the energy of these kind of radiations, right? So the radio frequencies are the higher in wavelength and lower in frequency. So, from this relationship, we can say that yes, if the wavelength is increasing, then the energy of these waves are decreasing. So, we can see that the energy of these radiations are the least. So, as we are going from radio waves, microwaves, infrared, visible, UV, X ray, and gamma rays, the energy is increasing dramatically. So, coming to the question, the amount of energy which is related to radio frequency radiations are very less. So, it is not able to excite a particular atom. For the excitation, we need ultraviolet radiant energy, which is related to this, that is 10 raised to power 15. To vibrate an atom, we need the energy which is equal to 10 raised to power 12. That is the infrared region. And to vibrate a molecule also. So, to affect the nuclear spin, the amount of energy which is required is very less. So, the radio frequency radiation is just sufficient to affect the nuclear spin of the atom, irrespective to excite an atom or to vibrate a molecule or an atom. So these three options are not the correct one. So we are getting the answer that affect the nuclear spin of an atom. So radio frequency radiations are just sufficient to affect the nuclear spin of a particular atom. So I hope this question is very much clear to you. So coming to the problem 2, if the number of protons or neutrons is even, the spin of the nucleus will be. The options are integral spin, half integral spin, zero, or the positive spin. So first we need to think that what is a nuclear spin. So nuclear spin is related to the nucleon composition, that is the number of protons and neutrons that is present in a nucleus, right? So first of all, we need to know that the nuclei which has odd mass, that is like 1h, that is having an odd mass, 13C, and 19F. These all having the odd mass number. So the nucleons are odd in number. So they have the fractional spins. So, but when we are considering the even mass nuclei, that is having an even mass number, that is 2H, 14N, then the odd number of protons and neutrons are available in the system. So these kind of nuclei have integral spins, that is equal to 1 or to 3 or 5. So even mass nuclei, that is having both the mass number and the atomic number even, then the nuclei has a zero spin, that is I is equal to 0. I is denoted as a nuclear spin number, right? So here we get to know that these kind of parameters are there to suggest the nuclear spin of a particular nucleus. So coming to the question, if the number of protons or neutrons is even, both are even for the spin of the nucleus, then the spin should be what? Now, from these parameters, we can say that yes, if both the mass number and the atomic number, that is both the protons and neutrons in the system, is even, then the the nuclear spin of the particular nuclei should be zero. So the correct option would be C, not A, B, or D. So I hope this question is clear. So the mass number of an atom is equal to number of protons and the neutrons. And in this case, we have both even, that is the even number of proton and even number of neutrons is present in the system. So the spin of the nucleus should be zero. So coming to the problem 3, in this case we have that all hydrogen atoms, the options are have the same resonance frequency, resonate at different frequency depending on their environment, are attached to the carbon, or resonate at about the same frequency as carbon. So what is which is the correct option we have to look at? So to resonate, basically a term that is chemical shift arises. So the hydrogen that is present in a nuclear or a system have different chemical environment, and and due to which they have different chemical shift. So the resonance frequency changes with the chemical environment of the nucleus. So which is basically measured as the chemical shift value, which is uh, which is arises as first of all when an external applied magnetic field is applied to a nucleus, then the electron density which is surrounding the nucleus is arising is generating a induced magnetic field. A secondary magnetic field is generated here, and due to which a shielding comes into play. So the electrons which are present around the nucleus generates a secondary magnetic field, and which is in direction opposite to the applied magnetic field. If if this generated induced magnetic field is very much high than the applied magnetic field, then a de-shielding in the chemical shift is observed. And if it is very small than the applied magnetic field, then the shielding of the nuclei is observed. So basically, the changing the distribution of the electrons around the nuclei affects the magnetic field that is experienced by the nucleus, because now it is not experiencing the full applied magnetic field which we are applying externally. It due to the presence of this induced magnetic field, some of the applied magnetic field is neutralizing. So it is not as effective as we are applying the magnetic field. So now the nucleus is not experiencing the whole magnetic field environment, but it is experiencing the magnetic field minus the secondary magnetic field that is generated due to the electron density present that surrounds the nucleus, right? So now it depends on the local magnetic field that experiences the nucleus, the frequency at which it resonates. As I have talked earlier, that if this magnetic field is very high, that is, the electron density is high, then the amount of this magnetic field increases. So this applied magnetic field now is very less, which is experienced by this nuclei. So now it feels a de-shielded environment, and now the frequency at which this particular nucleus is resonating is changes. So this variation in the frequency is known as the chemical shift. So it is denoted as a symbol of delta. So coming to a particular example here, if we consider this alkyl substituted carbons, here first of all this primary substituted carbon, here the alkyl substituents have plus I effect, due to which it increases the electron density at this particular carbon. And here the hydrogens which is connected to these carbons is feeling the induced magnetic field which is generating due to this alkyl group, and now it is not experiencing that much applied magnetic field which we have externally applied. So here, by increasing the substitution at these carbons, the plus I effect also increasing with this. So the electron density at this particular carbon is very high. That is why this hydrogens having increased chemical shift, that is from when we are going from here to here, the de-shielding is observed in the chemical shift. So the chemical shift value of this primary substituted carbon lies in between zero point 0.7 to 1.3, and the secondary substituted carbon lies in between the value of 1.2 to 1.4, and this tertiary substituted carbon protons resonate at the particular frequency of 1.4 to 1.7. So these are the chemical shift value which are represented in delta ppm, that is the parts per million. So this that is how the distribution of electron changes the resonant frequency of the nucleus. So coming to the question, now all the hydrogen atoms have the same resonance frequency? No, it is not, because the hydrogen atoms have different chemical environments, so they cannot resonate at a particular resonance frequency. Now the options here are attached to the carbons, but it is not obviously necessary that hydrogens are always connected to carbon. It can also be connected to a halogen or other atoms. So it resonates at about the same frequency as carbon? No, because the natural abundance and everything comes into play when we are talking about the resonance frequency. So it is not the same frequency at which the hydrogens are resonating as the carbon. So the option B, that is the resonate at different frequency depending on their environment, is the correct option, because all the hydrogen atom resonate at a particular chemical shift or a particular frequency depending on their environment, on the external environment which they are facing. As we have seen the example of this particular hydrogens which are connected to this tertiary substituted carbon, secondary and primary substituted carbons. So the option A is not the correct one. It doesn't resonate at the particular same frequency. It also always not necessary that the hydrogens are always attaching to the carbon only, and it is also not the same as the carbon. Resonate frequency is also not the same. So the option B is the correct one, that all the hydrogens are resonating at a different frequency depending on the chemical environment which they are facing. Right. So I hope this explanation is clear. Now coming to the problem 4. So the problem 4 consists like coupling causes the peaks in 1H NMR spectra to be split into. So coupling of the protons which are adjacent or vicinal to each other causes in the 1H NMR spectra to be split into. The options are two peaks, multiple peaks equal to number of hydrogen on the surrounding atom, multiple peaks equal to the number of surrounding carbon atoms, multiple peaks equal to number of hydrogen on surrounding atom plus 1. So here we have to first know that there is a general formula that we are used in the while calculating the multiplicity or the peaks which are arising in the 1H NMR spectra. So the formula is 2ni plus 1. That is, here I is the magnetic spin number of the given nucleus. So here we are talking about the hydrogens. So it is cut short to n plus 1. How? That here the I is equals to half for the hydrogen atom. In the case of hydrogen atom, the nuclear spin is half, that is the fractional nuclear spin. So the NMR, the formula which we are using here is the n plus 1. So now they are asking that the coupling uh, cause the NMR peaks to split into which of the options, like multiple peaks equal to the number of hydrogens on surrounding atom plus 1, or the multiple peaks equal to number of hydrogens, number of surrounding carbon atoms. So here we are not talking about the carbon atom, or carbon atom are not playing role in the splitting of the particular 1H NMR. So this option is although very much wrong. Two peaks, it is not always necessary that the coupling is splitting the peaks into two only. It is not always necessary, as we are going to discuss some problems in shortly, so we will get to know about this. So The B option is multiple peaks equal to number of hydrogen on surrounding atom. That is this. Number of hydrogen on surrounding atom. N is the number of hydrogens which are present on the surrounding carbons. But it is also the value that is present here, that is plus 1. So the option D will be the correct one irrespective of B, because we have n plus 1 here. So the number of hydrogen that is present on the adjacent nuclei plus 1 will be the coupling, will be the peaks that is arising due to the coupling of the different carbon, different hydrogens. So so this is the explanation of the coupling that is causing in the 1H NMR, and as it is not because of the carbon atom, so it is not C could not be a correct option. And two peaks is always not necessary. Multiple peaks of equal to the number of hydrogen atom or surrounding atom is very much clear, but the integer here, that is plus 1, is also can't be neglected. So the D option is the correct one. I hope it is clear. So now coming to the problem 5. So what is shielding in NMR? So, as we have discussed, that there is a particular applied magnetic field which is applied on the nucleus, and then the electron density which is nearby of that nucleus just oppose the applied magnetic field by generating a secondary induced magnetic field. So, this by taking this much information in hand, we are discussing this problem here. The options are using a curved piece of metal to block an opponent attack. No, definitely not. And the option B comprises the putting metal around an RF source, that is the radio frequency source. Option C is when the magnetic moment of an atom blocks the full induced magnetic field from surrounding nuclei. And the option D is blocking parts of molecule from radio frequency radiations. So here first we have to know that what is shielding in the NMR. So here, when, as we have discussed, that the applied magnetic field generates an induced magnetic field around the nuclei. So here, if this induced magnetic field is higher than this applied magnetic field, then de-shielding is observed. So it requires a lower applied field strength. So it can also done by increasing the induced magnetic field. So if the electron density around this nucleus is higher, then this induced magnetic value is increasing significantly. So it is increasing that this applied magnetic field. So now the nuclei is not facing that much applied magnetic field that we has externally applied. Now it is facing the applied magnetic field which is equal to the external magnetic field applied minus the induced magnetic field which is generated. So in that case, a de-shielding is observed, and the chemical shift value is downfield. Now it is going to downfield. Downfield here is suggesting that the chemical shift value is increasing. When this induced magnetic field is not that much high, the electron density is not so good here around the nucleus. So applied magnetic field strength increases. So now the chemical shift value in this case is now not increasing, irrespective, it is decreasing. So it is higher field. So one has to keep in mind that this de-shielded region or the upfield or the low field doesn't mean like that. The lower field means that the chemical shift has a higher value, but the higher field means that the chemical shift value is low. So one has to keep this in the mind, so not to get confused with that terms. So now coming to the question, what is shielding in NMR? So as we have seen that when the magnetic moment of an atom blocks the full induced magnetic field from the surrounding nuclei, then the shielding comes into play. And if the vice versa is there, that the magnetic moment of an atom is less than the induced magnetic field which is generated around the nuclei, then a de-shielding case is observed in the NMR. So the option C will be the right one. Using a curved piece of metal to block an opponent or attack is not the correct option. Putting a metal around a radio frequency source is also not going to give you a shielding in NMR. And blocking the parts of a molecule from radio frequency radiation is also not the case. So I hope the explanation is clear to all of you. Now coming to the problem 6. The distance between the center of the peak of a doublet is called as. So here we are discussing about a peak that is a doublet. So the distance between the peak of a doublet is known as what? So first option is the coupling constant, second is the spin constant, C is the spin-spin coupling, D is the chemical shift. Chemical shift is, we have discussed that it is not the distance between the center of the peak of a doublet. Irrespective, it is the resonance frequency of the, it is the frequency at which the nuclei resonance in the different chemical shift. So it is not the answer. So now we have to discuss that amongst three, which is the correct option. So now coming to the coupling constant. Now here we have an example that we are discussing that a doublet in which the distance between two peaks is considered as what? Now when we discuss this doublet, the chemical shift value at this doublet is 5.310 and 5.286. So the distance or the difference between two values is known as what we have to discuss here. So the coupling constant here is the distance between the peaks in a given multiplet and is the measure of a magnitude of splitting effect. So a splitting is causing to a peak to form a doublet, and now the distance between these two peaks, that is a doublet, is known as a coupling constant. So here the coupling constant is referred as a symbol J and is expressed in hertz. So here if we have to calculate the difference between these two peaks, that is the 5.310 and 5.2866, that is the chemical shift value, and now we have to find the difference between these two peaks. So the difference between these two peaks will be is like dppm, and it which is multiplied by this operator frequency, and here we can get the value of the coupling constant, which is around somewhat around 7 hertz in this particular case. So we can say the distance between the center of the peaks of a doublet, when we have to calculate it, it is known as a coupling constant. It is not for doublet. It is all the general peaks that is splitting is the distance between the center of the peaks is known as the coupling constant value. So the A option would be the correct one, not the spin constant, not the spin-spin coupling is the correct one. So how to calculate a coupling constant we have seen that in this particular case, when we are differencing between this chemical shift values and multiplying it with the operator frequency, that is a 300 megahertz here, we will get the value of the coupling constant in hertz. So I hope this is clear. So now coming to the problem 7. So here, in this case, first of all, they have asked that the 1H NMR spectrum of CH3O, CHCl, CH2Cl will exhibit what? A 3 proton doublet, a 1
Ma'am,
proton.
excuse me, what?
Sorry.
I want to know the answer first. Which is the option? I didn't get it actually.
Okay, okay,
That
okay.
part.
Okay. Wait. So you are asking about the question 6?
Yes, yes.
Okay. So here, uh, actually the question is the distance between the center of peak of a doublet is called as. So first we have to know that the coupling constant, spin coupling, or the chemical shift. These what are these? So we have discussed about the chemical shift value, right? That this is the. I hope you got the chemical shift, right?
Yes, yes.
Okay. So here, just see this example. Here, this is a doublet. Okay.
Hmm.
Now we have this chemical shift like 5.310 at which this resonating, and at 5.286, that is the chemical shift value of this doublet. Okay. Now they are asking that that the distance between the center of the peaks of a doublet is what. So if we just minus these two chemical shift value, that is the difference. How you are going to get a difference? You are when you are minusing this particular chemical shift value, then you got the difference between this chemical shift value and the distance between the two doublet. Okay, the two doublet peaks as you are showing here, if you have to calculate the distance between these peaks, you first have to difference the chemical shift value of these peaks. Okay, so here we have discussed that the coupling constant is the distance between the two peaks in a given multiplet. Basically, when you difference this particular chemical shift and just multiply it with the spectrometer frequency, that is the 300 megahertz in this case, then you got the coupling constant value that is in hertz. So the difference which we are getting after just minus between this 5.310 5.286 chemical shift, then the we are getting the coupling constant value. So it actually doesn't vary on the it is doesn't depends on the electromagnetic radiation or electric field. It remains the constant throughout. So it is not the chemical shift. When you are just applying the magnetic field and you are getting the chemical shift value, it may vary if you are increasing or decreasing the chemical shift, electromagnetic radiation. But in the case of coupling constant, it always keeps the same. So if you are changing this spectrometer operator frequency, if you are increasing it or decreasing it, the chemical shift value can change, but the coupling constant value will remains the same. So coupling constant is the difference between these two chemical shift into the instrument frequency. So here, when we are discussing the distance between the center of two peak of a doublet, it is only the coupling constant which is reflected from that particular distance. Are you getting my point now?
Yes, yes, thank you.
Okay, thank you. So, shall I start with the problem 7?
Yes, ma'am.
Okay. So, in the problem 7, here they have asked that how the 1H NMR spectrum of this molecule will exhibit what? So as I have seen, I have showed you that there is a 2Ni plus 1 rule which is operative in this 1H NMR spectrum. Okay. So here we have reduced it to N plus 1 rule as I is equals to half for hydrogens. And in 1H NMR we are already talking about the hydrogen atom. Okay. So we can reduce it to N plus 1. Is it clear? So here they are asking that what is the 1H NMR spectrum of this particular species. I have expanded this particular chemical formula here. So here methyl CH3O CHCl CH2Cl is the chemical formula. So when we are discussing about this hydrogen, just first discuss about this hydrogen. Okay, so it is connected to carbon, and although in the adjacent there is no hydrogen present in the adjacent. Okay, and here in the rule we have discussed that n is the number of hydrogen that is present adjacent to the proton. Okay, so here in this case, in the case of this hydrogen, there is no hydrogen that is present at this adjacent position. So now there is no proton which is present in the vicinity to split this particular proton. So it is showing a the singlet. Are you getting how it is showing a singlet? Because there is no hydrogen which is present in the vicinity of this particular hydrogen, and there is no hydrogen, so it cannot split this proton into further peaks. So in the 1H NMR, you will be showing a single peak for this hydrogen only, and it is not further split by any of the proton because on the edges and there is no hydrogen present. Okay, so we are seeing a singlet for this particular proton. So methyl is going to give you a singlet. So now coming to this proton, so here this proton has two adjacent neighboring protons which is present. Okay, so these two protons are equivalent or non-equivalent. First, we have to look at this. So if they are equivalent, then they all together will split the signal of this particular hydrogen. But if they are non-equivalent, then this proton will split this proton in a doublet, and again this proton is again split this proton in a doublet. So what you are seeing here is doublet of a doublet. Okay, if these two protons are non-equivalent. Are you getting my point? Non-equivalent in the sense they have different chemical environments surround them. Okay, so if this proton, see it, look at this proton. It has hydrogen and chlorine, which is surrounding. Okay, and look at this hydrogen. It has chlorine and hydrogen, which is surrounding. So they are equivalent. They are non. Cannot consider it as a non-equivalent because the surroundings of these protons are same. So if these protons are same, then they all together show a splitting on this particular hydrogen. So if you are seeing in NMR up singlet for this proton, that is HB, I am considering it as a HB, okay, for your sake. So if you are seeing a singlet for HB, okay, then as these two protons are coming in the vicinity of this particular hydrogen, and these two are equivalent, so they sum up and then split this particular peak. So as we have discussed that n plus 1 is the rule, n is the number of hydrogen atom that is present in the vicinity. So here the number of hydrogen atoms are 1 and 2. 2 are the hydrogen atoms, okay. So it will be showing a triplet for this particular species. Here you can see that as these are the two hydrogens, then plus 1 will get you a 3. Okay, is it clear? You are getting a
Yes,
3. Yeah, so you are getting a 3. So this particular peak of HB is now splitted in a triplet just because of the proton that is present in the vicinity of this proton. Okay, because these are two, that is why according to the n plus rule, it is splitting into a triplet, not a doublet. Okay, if these are non-equivalent, we can further discuss it in the coming lecture that what are the non-equivalent proton, what are the equivalent proton. So here you first have to consider on the equivalent and on the basics. Okay, so when you got to know the basics now, then it is very much easy for you guys to understand what is the difference in the equivalent and non-equivalent protons and how they split the particular signal differently. Okay, so here these two protons are similar. That is why it is splitting this HB signal into a triplet according to the n plus rule. And now coming to this HC, I am terming this two protons HC because these are same. So now these two proton is splitted as this is a signal of these two proton HC. Okay, let's say that it is a signal of these two protons HC. Now here HB is splitting these two signals, that is these signals, into a doublet because it is only a one proton that is present in the vicinity or the adjacent to these HC protons. That is why when we are applying the n plus 1 rule, now HB is the only proton that is present in the environment and a vicinity of these HC protons. So that is why as the term N here is 1. So 1 plus 1 will give you a doublet, that is 2. Okay. So now this particular peak, which seems to be like this in NMR, is further splitted into a doublet. Now you will be seeing this proton, that is HC, splitted into a doublet. So in the NMR, you will see this kind of pattern. And for HB, you will be seeing this kind of pattern. That is a triplet. And for HA, as I am taking it as a HA, right? I am taking it as a H. So if methyl proton is HA, then I have discussed that there is no proton that is present in the vicinity of these three hydrogen as it is equivalent. You guys know that methyl protons are same. It is not that three protons are different and have different environment. So these are also the equivalent protons. Anyone is, just give me a second. Okay. Okay. Do you guys get my point that this proton that is present on the methyl, now if we are considering it is a HA, then these three protons, as this doesn't have any further hydrogen to split this signal into some or multiplicity, this is the singlet which is forming for this particular HA. As there are no hydrogen present in the adjacent, then this particular methyl will be showing you a singlet. So this HB is splitted into a triplet because of these HC protons that are present at the adjacent carbon, and these Hc protons in turn is splitted by this hydrogen only. So, according to the n plus rule, 1 plus 1 will give you a doublet on these Hc proton, and for this Hb proton, we are going to get a triplet, and for this Ha protons, we are going to get a singlet. So, is this clear to all of you?
Yes.
Okay. So the options which they have given is a three proton doublet. So it is not the case here, right? We are not going to get a three proton doublet anywhere because there are no hydrogen which is present on this particular oxygen. Okay. So it is not the correct option, as we can see from the first thing, that it is not going to give a doublet. So now a three proton singlet and one proton singlet, a two proton doublet. So here in this case, we are going to get a singlet of this three protons, a triplet for these one proton, and a doublet for these two protons. So the option which is matching to this kind of thing is the correct option. So we are seeing here the three proton singlet, okay, which is correct. Now coming to the one proton singlet. So here we have a proton, but it is not showing a singlet, right? It is showing a triplet. So it is not the correct option. Now, coming to the option D, a three proton triplet, which is very much wrong because we cannot see a three proton triplet here. Okay, as we have mentioned that there is no hydrogen which can cause the splitting of these methyl protons. Okay, so this is also not the correct option. Now coming to the option C, a three proton singlet. Three proton singlet. Okay, fine. It is the criteria. Now coming to the one proton triplet. It is also right that in the case of one proton HB we are getting a triplet. Okay. Now coming to a two proton doublet. Yes. In the case of HC, these are the two protons, right? And we are getting a doublet. So this is the correct option, that is HC. Okay. Option C is the correct one. I hope this much is very much clear to all of you. And if it is not clear, then please ask me. Okay. So, shall I proceed to the problem 8?
Yes, ma'am.
Okay.
Ma'am, is this the assignment 0?
Sorry?
These are the questions for assignment 0.
Yeah.
Because assignment 1, there was a PDF file.
Yeah, yeah. For the assignment one, it is not, it is the basic questions which I have previously actually discussed. You have seen my video, right?
Yes.
Okay. So there I have just given you the answer of that particular assignment, and this is the assignment 2. Okay, this is not the assignment 1. It is the assignment 2, which I am just uploading this video on the portal. I haven't uploaded it till now. So this is the particular solutions. So you can,
Answers where will I get?
sorry?
And the answers for the assignment 1?
No, no, these answer is for assignment 2 only. The assignment 1 have their own answers.
One answers that you discussed.
Yeah, in the assignment 1 I have discussed the answer in the video, right?
Okay.
Oh yeah, you have to look at that video. If you are not able to cope that
That means in the
answers,
week 1, I'll get that video.
yeah, yeah. In the week 1,
Okay.
actually there is a channel, right? You guys know about that channel, right?
Yes, yes.
So you can go there and you can take the week 0 assignment. I have termed it as a week 0, okay? So you can click on that video and you can go through that particular problem. If it is not clear,
Okay.
then just come to me and I will show it to you again, okay?
Okay, and another thing, Tuesday there is the organic class which is overlapping with quantum.
Okay, overlapping with
Yeah.
quantum.
Yes.
Okay, actually, that thing I haven't received till now. Actually, that was not the thing which I have handled. It is the NPTEL people and all that particular things is handled by them. So I can't do anything for that. If you guys can mail them, or if you want me to mail them, then I can do that. Okay. So whatever you say, I will do that.
Okay, ma'am, if you mail, then it will be for us.
Sorry.
Because the same 6 to 7 quant also, and 6 to 7 is organic class also.
Okay, 6 to 7. But mine was to 3 to 4, right? You are not asking about me.
And then means it's the same means organic class they give two timings. One is the Sunday 3 to 4, and
Yeah.
one is the Tuesday 6 to 7.
Okay, 6 to 7. Okay, so that class will be the I think okay. Monday 6 to 7. Okay, there is another TA, right? Which is taking that particular slot. I think.
That is, I think so. That is organic mechanism class.
Yeah, that is not about the introductory organic chemistry. Organic mechanism will be there, right? Because in another TA, which is of this particular course, is taking the classes on Tuesday, so it is not about Monday. Okay.
Okay.
Okay, so you can ask them on the particular class because it is not
To
my
change
course,
the
so I
schedule.
can't. Okay,
Okay.
okay. So this much is clear to all of you, right?
Yes.
Okay. So I'm proceeding with problem 8. So here, which of the following 1H NMR spectrum of compound with molecular formula C4H9NO2 shows a delta 5.3 rhod 1H, 4.1 quartet of 2H, 2.8 doublet of 3H, and 1.2 triplet for 3H, right? So we have to look at the particular molecular structures of the compounds to answer this problem. Okay. So here we have given they have given the NMR data, that is delta is the chemical shift values of the particular protons that is present in that particular compound. So they have given us the data. In the case like here the 5.30 chemical shift is the broad spectrum of 1H, and 4.1 is the quartet which is coming for the two hydrogens, and here 2.8 a doublet which is coming for three hydrogens, and 1.20 at a triplet that is coming for three hydrogens, right? So previously we have seen the chemical structure and we are assigning the doublet and triplet and quartet kind of thing. But here in this problem, we have to figure out which is the chemical structure which is correct according to this particular chemical shift values. Okay. Now we can go to we can start with this particular first. Here the methyl protons, as we seen previously that these three hydrogen protons are equivalent, and now if they are showing a singlet, if they are showing a singlet, then the nitrogen proton, that is NH, here the methyl has a adjacent proton which can split the particular signal for the methyl protons into further multiplicity. And multiplicity can be n plus 1, which we have seen previously. This is the particular rule which is applicable in the 1H NMR everywhere where we are talking about hydrogens only. Because I value changes if we are talking with about some other atom. But in the 1H NMR, we are always talking about the hydrogen only. So I is always be half. So 2Ni plus 1 rule can be cut short to N plus 1. Okay. So here the methyl protons is splitted because of this hydrogen which is present on the nitrogen, right? So here if N plus rule is applicable, then there is only one proton that is present in the vicinity. Now, it can show, according to N plus law, it would be showing a doublet. It splits the particular signal into a doublet. Is it clear? So now the methyl protons are showing a doublet, a clear cut doublet. Now coming to this nitrogen protons. Here, nitrogen protons. Now here they will be showing a broad spectrum. Guys, when we discuss in the previous, or we will be discussing in the lectures. Now then you will get to know that the OH peaks and the NH peaks in the NMR is broad. They are never be sharp due to the spin relaxation, spin lattice relaxation. We will be discussing that parameters in the coming lectures. Okay, so don't worry about that. I will let you know everything about this NMR. But here now I am just saying that NH proton will give you a broad signal rather than a sharp signal due to spin lattice and spin relaxation, which will be we are discussing in the next series. Okay, so don't worry about that terms. Now, coming to this problem, NH, the proton of hydrogen will be showing you a broad signal of one proton. It is not splitted by these kind of protons because here also the proton is cannot be split. And here in the carbonyl case, there are no protons that can split this particular hydrogen. So it is showing a broad singlet. Broad because of the relaxations. I will let you know about that relaxations, okay? So now coming to another carbon which is having hydrogen, that is the CH2 here. So here these two protons are surrounded by these three. Okay. Now on the left hand side there are no protons, but the right hand side have three protons. So you have to keep in mind that if it is the case and these are equivalent, then we have to follow the n plus 1 rule. Now here, according to the n plus 1 rule, if these are the three protons, then it will be splitting this particular proton, let it be HA, okay, these proton into a quartet because 3 plus 1 will give you a 4. That is a quartet. Okay, just keep in mind that n plus rule is very much effective in 1HS NMR. Okay, so you will get every answer according to that. So the splitting always depends on that particular rule. So CH2 signal will be splitted into a quartet because there are three proton that is present at the adjacent, and when you apply the n plus 1 rule, that would be the 3 plus 1, that is 4. So we are getting a quartet. We are getting a quartet for this particular CH2. And here also, in the case of methyl, there are two proton adjacent. So how much multiplicity should we expect from this? Can anyone tell me that how much will be the multiplicity of this particular methyl if it is present in these about these two protons surrounding? Then how much splitting it would be causing for this particular methyl group? Can anyone tell? See, guys, if you are discussing about this methyl group, okay?
Two,
Sorry,
three, the
yeah,
side one,
yeah, it could be a triplet, okay?
triplet.
Yeah, it will be a triplet. So methyl, for the methyl case, we are getting a triplet because there are two protons that are adjacent to this particular carbon, and according to the n plus rule, when we applied that, then these are the two protons, and 2 plus 1 will get you a 3. That is a triplet. Okay. So we have assigned all the multiplicities, right? So now coming to the chemical shift values, guys, I have told you that if there is some electron density, if there are some electronegative atoms, then they push electron towards it. Okay, if the electron density of that particular around that particular nuclei comes down, then the downfield shift will be seen. Okay, so in this case particularly, methyl protons, here guys see, the methyl protons is seeing a doublet. Okay, here also it is a doublet, but when we goes to this particular molecule for the methyl, as we have seen earlier, that there is no proton that is attached on the adjacent carbon, so it would be going to give a singlet. Coming to these CH2, as these are the equivalent, now here also there is no proton, here also there is no proton to split this particular signal into further multiplicity. So these protons, these CH2 will also be giving you a singlet only because there are no protons that are present at the adjacent. Okay, and here also, and in the case of NH, I have told you that these are going to give you a sharp signal. So it is also giving you a singlet. In the case of methyl, it is splitted because of this proton into a doublet, as we have seen in this case. Okay, so we have assigned the particular multiplicity for this compound. Now coming to the compound 3, here methyl protons. Because of this, it will be giving you a triplet because two protons are adjacent. Now
Edges.
for this CH2, you are going to get a quartet.
Correct.
Yeah, you're going to get a quartet. Okay, this again will give you a sharp singlet. Okay, now for this methyl, there is no proton around this, so it is also giving you a singlet. Fine. Now coming to the compound 4, in the case of this methyl, you are going to get a triplet.
Triplet.
Yeah, the quartet here for this.
Then quadrate.
Yeah. Then what
Then
we?
for the singlet.
Yeah,
CH2.
very good. Singlet. And for this amine, we are also getting the singlet. Okay. So now, first of
Yes.
all, we have first thinking that we have to match the multiplicity of these compounds to the particular data which they have given. Okay. So which multiplicity are matching? So let's just see about that. For three proton, for the three proton, they are getting a doublet. Okay. We are getting a doublet for this case. Now for one proton, they are getting a singlet, broad singlet. Okay, we are getting for that thing. Now for two protons, they are getting a quartet. Yes, we are getting also a quartet. Now for three protons, they are getting a triplet. Okay, yes, we are getting the triplet. We would assign that which is which, because there are two methyl. You might get confused that which methyl we are talking about here, right? From the multiplicity, you can say, but you have to know about the chemical shift also. So here we are just focusing on the multiplicity because in the later lectures you will get to know about the chemical shift, how it varies. Okay, so just worry about the multiplicity till now. So the compound A is compatible, okay, according to the multiplicities. Now coming to compound B, a methyl, that is a 3H singlet. Are you supposed to get that? No, there is no
No.
option, right? So clear cut, this is not the required molecule. Now coming to compound C, a triplet for three protons, yeah, it is there. A quartet for two protons, yes, it is there. A NH, yes, it is there. A broad signal for one proton. Now, for the methyl, it is coming to be singlet. Is it the case? No, right? There is no
No.
peak which is giving a singlet for three protons. So, this is also not the answer. Now, here coming to the fourth option, the methyl group. Methyl group is giving a triplet for 3H. Yes, it is giving a quartet for 2H. Yes, we have it. But we don't have this. A singlet for two protons. Do we have this? No. Right? So,
A is the option.
sorry?
A is the option.
Yeah, A is the option. So we are not having this kind of multiplicity in this particular case. So A is the correct option which we are looking at. So A would be the correct option. Okay. Don't worry about the chemical shift. I will let you know about the chemical shift in the later lectures. Okay. So coming to the problem 9. So a proton Hb is coupled to four equivalent protons of Ha. Then the multiplicity and the relative intensity of lines in the signal Hb is a doublet, a triplet, a quintet, or a quartet. If you guys are able to answer those particular questions, you can definitely answer this particular question because it is a very simple question. So what they are saying, see what they are saying. They are saying that the Hb protons, if I would make a Hb proton, okay, let me just make it so that it would be very much clear to all of you. Okay, yes. So this is what Ha protons. So let's say these are the four Ha protons on the another carbon atom or something like that. See, Hb proton is coupled to four equivalent proton Ha. What does this mean? See, Hb has four equivalent protons that are surrounding in its environment. Okay, So that is why it is coupling with HB. Okay, if HA is not very far away, then how it is going to couple with HB? Okay, it is not coupling with HB then. But here they are saying that HB is coupled with four equivalent proton of HA. It could be anything, right? So HB, if it is having four protons, and sorry, HA, if it is having the four protons, and HB, it is getting coupled with this HA, then what is the multiplicity? So again, n plus 1 rule comes into your mind, and you can surely say that yes, four equivalent protons are
Third
there.
option.
Sorry,
Third one.
third one, yes, it would be the quintet. Okay, because when we applied the n plus 1 rule, then n would be 4. Okay, 4 plus 1, that would be a 5. So 5 is represent the quintet. So for your sake, I will show this. See, here different multiplicity and n plus 1 rule is given. Here we have HA which is surrounded by HB. Okay, if we say that yes, we have to see that what is the multiplicity of HA, then it is in the vicinity of only one proton, HB. So it would be a doublet according to n plus 1 rule. HB is 1 plus 1 will give you a doublet. In that case also, if it is 2 protons that is in vicinity with HA, then it will be going to give you a triplet because of the n plus 1 rule. And here HA is equivalent, HB is equivalent, two protons are there, it will also giving you a triplet. Because if we are talking about HA, okay, just remind this, if we are talking about HB, then we have to see that how much HA equivalent protons are there to couple with HB. If it is 2 here, then according to n plus 1 rule, it would be a triplet. Okay, and after that we have to see the quartet. Here how this quartet is coming. HA is being coupled with these three protons of HB, which is splitting the signal of this HA into further four. That is a quartet. In our case also, we have HA which is surrounded by this with four protons. So in that case, we are getting 4 plus 1, that is 5. That is a quintet. So guys, here the multiplicity we got to know that it is a quintet, but how we are going to get the intensities, it is also a particular very important question. So you have to just you have to see this triangle. So this is nothing but a Pascal's triangle, which is operative in the intensity calculations of 1 HNMR. So when you have to see the intensity, you have to just follow this particular Pascal triangle. So I will advise you that please just remember this triangle so that we can further uh, solve the problems according to that particular thing. So I would have remind you again and again that this is the Pascal triangle which we have discussed. So please just keep this triangle in mind so that it is very easy for you to understand the relative concepts. So in the case of a when n is equal to 0, n is nothing but the number of hydrogen that is present in the vicinity. So if it is 0, then we are going to get a singlet, as we have seen that for the methyl protons we are getting a singlet right here. Yes. So if it is 0, then we are getting a singlet, then the intensity would be 1. Intensity would be 1. Intensity would be 1. Okay. But if doublet is there, then intensity divided into 1 is to 1. Then the two signals would have same intensity. The two doublet signal would have same intensity. When we are discussing about a triplet, then the intensity, sorry. Then the intensity would be like this. Okay, then it is 1 is to 2 is to 1. So A and C peak is similar intensity, but the middle peak having the twice intensity. So you have to just keep this triangle in mind. Okay, so when we are discussing here about the quintet, okay, so here for the quintet, we have 1 is to 4 is to 6 is to 4 is to 1 intensity. So if you have knowledge of this particular triangle, then you can easily answer this. Okay, so just remember this triangle, and the option which is correct here is quintet with the intensity of 1 is to 4 is to 6 is to 4 is to 1. So is it clear for everyone?
Yes, ma'am.
Okay. So I'm coming to the next problem. That is the last problem of this session, guys. So I will be meeting you in the next session. So with the more problems and more concept-based questions. So just have the look on this particular video again, so that if anything disturbs you or anything doesn't understand, then you can come to me and I will answer it for sure. Okay. So in the problem 10, they are asking which of the following isotope is NMR inactive. So the options are 1H, 13C, 31P, 16O. Okay, guys. So here they are asking,
First,
sorry,
first one is answer.
yeah, first one is the answer. No, 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 no. First one is not the answer.
No, no, first one is I'm telling. C,
See, are you
31P.
okay? You are telling the 31P is the answer.
Yes.
Okay. Okay, so let's see which is the answer. Okay, so here, which they are asking that which NMR isotope is inactive. Okay, so we have seen that we are discussing about the 1H so far. Okay, so it can't be inactive. Okay, it is somewhat which is NMR active, and 13C also we have talked. It is not NMR inactive. How we are going to give the suggestion or the clarification of this? Now see, we have discussed something like this, that the odd mass nuclei having the fractional spins, and the nuclei which having the zero spin na, that are inactive, that are NMR inactive. If they don't have a spin, how they are going to align with the external magnetic field, how they are opposing the external magnetic field? Are you getting my concept? If the spin of the nuclei is zero, although, then how it is changing the spins or aligning in the direction of magnetic field which we are applying? Okay, so that is why, if for the NMR inactive, the case should be that I, that is the spin number, should be zero. So for this particular molecules, here 1H, the mass number is 1. So see, guys, if the odd mass nuclei is there, then the fractional spins are there. So for the 1H, we have I is equal to half. That is the fractional spin. So it is although not the NMR inactive. So it is not the answer, because it is NMR active. Okay. Just keep this concept also in the mind. You will get very much clear about these particular basic concepts. Okay. So if even mass nuclei composed of odd number of protons and neutrons have integral spins. See, even mass nuclei. So if we have even mass like 2H, 14N, then the spin should be integral. But even mass is there. But if we talk about hydrogen, atomic number is 1. Okay, we have known that the atomic number is 1. So if we have even mass for a nuclei and odd atomic number, then the integral spins are we face a integral spin. Then the spins are not rational, it would be integrals. But if both the atomic number and the mass number in a nuclei is even, then they possess a zero spin, guys. So you have to keep this kind of thing in mind, that if both the mass number and atomic number of a nuclei is even, then it would not going to give you a NMR active species. It is not going to give you any spin. It is not going to align in the external magnetic field which you are applying. Okay, it is not giving you anything. Just keep that thing please in the mind. So, as here we can see that 1H, here odd mass number is there and odd atomic number is there. So it has a fractional spin. So it is not an MR inactive. In the case of 13C, you can say that it is odd mass number and even atomic number. These kind of species is also having the rational spins. So fractional spins are there, so that is why it is not also NMR inactive. It is also active NMR. 31P, in the case of 31P now, what happens is, here it has an odd mass number. See, odd mass number. And we have discussed that odd mass nuclei are not NMR inactive, guys. So please that keep that thing in mind, that 31P is not the answer. It is not NMR inactive. Although 16 oxygen, 16O, that is the oxygen. When you go for the oxygen, you will get to know that yes, the even mass number is there, and although even atomic number is there, because oxygen have an even atomic number. Okay, as we have discussed and as we know that oxygen have a even atomic number and the mass number, so both are even, then we can say that it has a zero spin. If it has a zero spin, then it is NMR inactive, not an active species, because it is not going to align in the external magnetic field. It is not going to give you a peak or what something. Nothing is given by this 16O isotope. Okay, so it is the correct answer. So one can suggest this that 16O is NMR inactive because the magnetic spins of this particular species is zero. Okay, anyone has any problem in this particular explanation?
No, ma'am.
Okay, so now you got to know now why D is the correct option, not the C.
Yes, yes, it's
Okay,
clear.
okay, okay. So these are the problems for today. So I will be meeting you in the next week, Sunday 3 to 4. So please be there, and I hope this session is very beneficial for you. And thank you so much for attending it and listening me patiently. Thank you so much.
Thank you, ma'am. Ma'am, you can tell the organic mechanism to change the class for 6 to 7 on Tuesday.
Okay. So you want it
They
to
can
be
take on Monday. Monday 6 to 7 there is no class.
okay. So I will talk to them if possible. Then I will let you know in the next session. Okay.
Okay.
Okay. Thank you.
Thank you.